Welcome everyone to our 6th replication workshops. We are almost at the end. Today our focus will be on energy grid and infrastructure. A big thank you to Pio Lombardi from Fraunhofer Institute for organizing today's session. Just a few organization bits. First, we will record today's session, so please prepare for that. The second rule, please wait with all the questions till the end. We will have a prepared time for Q&A. If you're afraid of forgetting the question, you can always write it in the chat, and I will remember and make sure to get back to them at the last session. So I don't want to extend any more longer. I give the floor to Ms. Andrea Dornhofer, the head of the Energy Project Department in Weiz Energy and Innovation Center, with the presentation on good practice from the municipality of Thannhausen, direct connect grid for the direct share of PV electricity. Ms. Andrea?
Yeah, hello. Yeah, hello. Andrea Dornhofer is my name, and I'm working for the Weiz Energy and Innovation Center, and I would like to show you a best practice example from our region here with the project So Weit Connected, where we're testing a multiple PV use of one PV plant with a power of 29 kilowatt peak to provide 100% renewable energy to 7 users with an own electrical network. So next slide. This project is funded by the national government of Austria under the framework of the project City of Future. We started with the project in October 2018, and it will last till September 2022. We have fundings of around 300,000 euro for this project, and the coordinator here is the municipality of Thannhausen. It's a very small municipality with only 2,300 inhabitants. We have the project partner EOS Power Solutions. They are responsible for the energy management system and the whole regulation of this direct grid. The Forward Energy Research company, they are making all simulations and life cycle costs. And also we have on board the energy grid operator of Styria. It's very necessary to have the grid operator of the Styrian grid within such a project, because without them it's not possible to implement an own direct grid system here in Austria and in Weiz. What are the targets of our So Weit Connected project? It should be a direct grid system which provides electricity from 1 PV to 7 users which are close in the neighborhood. All users are also connected to the official grid of the grid operator of our Styrian network, and they have also the PV electricity from our system. This system is the first realized system in Europe with more than one user is connected to an own grid. That's also in the beginning of the project we also discussed about the local energy community and going through the net of the grid operator, but the law wasn't so fixed and isn't so fixed so far. So we calculated the system with our own network, and now we are still in operation, and now in end of June we will going in real operation with this system. What is the status of the project? On the right side you can see the picture and you can see the whole area of our system. We have connected one family house, a multiple family house, and 4 small companies which get their PV power from this PV plant. Here you can see it will be on a building of the municipality with the power of 29 kilowatt peak, so we can gain about 30,000 kilowatt hours coming from this PV plant. The PV system is already installed since last week. The diggings and all the grids are under the earth now. It's finished since yesterday. The energy management system is in operation and several regulations are implemented in each household. Several components for the measuring and the monitoring system will be finished in about 2 or 3 weeks. The tariffs for the users are fixed. Each user will have a special tariff for their electricity, which they get from the system. We have also a calculation system which the municipality do then with each users. The monitoring system, the finish of the monitoring system is under construction, and all contracts are signed by the users so far. What are the electricity consumption of each user, or what can they get from the PV plant? They can get about a quarter of their normal electricity consumption. So if an example, one company, normally they have an electricity consumption of about 12,000 kilowatt hours per year. So they can get about 3,000 from their own grid of 1,000, and the rest of the consumption they get normally from the energy grid of Styria. So we have 100% self-use of the PV from the municipality, sharing through 7 users. The tariff which we calculated for each user will be 8.14 cents per kilowatt hour, excluding the taxes, and so it's much lower than they pay for their electricity coming from the official grid of Styria. What are this in euros, or what the savings or the calculated savings per year for each user? It depends between 25 euros per user and up to 170 euros per user, which they can save per year concerning their electricity costs. We had the first idea was to have that each user also invest a bit within this system, but they don't want, because the risk was them too high. They don't want to invest, and then they were not sure if the system will work, and so we fixed with them that they invest nothing and get this 8 cents for the kilowatt hour, which they get from the system. So some impressions from the Thannhausen area, the PV system and the diggings. Now it's finished. We also have water lines and also district heating lines, and also the glass fiber power, which we also with this project also was connected to the households. In the next picture is at a 7, because every house has an own grid coming from the PV, 7 own grids to each user. That is the law that you have to provide. Each user have to be an own grid from the PV to their households. There you can see, and the work through here you can see the PV panels and the new 29 kilowatt peak, which are finished since 2 days ago, and we hope we can get in full operation until July 2021. Thank you for your attention. It was a quite short presentation, and we can answer several questions after the other presentations. Thank you in the meantime.
Thank you so much. If you have any questions, please write it in the chat or keep for the last session. I will now give the floor to Dr. Pio Lombardi, researcher at Fraunhofer Institute for Factory Operation and Automation, with the presentation on business models for energy storage integration.
Okay, so thank you, Zaneta, for the introduction. Good afternoon to everybody. I'm going to show you some experience that we have done at Fraunhofer Institute at the University of Applied Science about the use or usage of energy storage system. The experience that we have collected has been also done with Dr. Wenge, which we present at the end of this workshop. So one of the main aspects which interest the investors or the user which want to install storage system is the business models, or how which kind of business model may be developed for storage system. And this presentation deals with that. So first of all, I will give you an overview of why we need storage system. I think that is obvious. We know that in Europe, we aim to decarbonize the power system, which means that we will generate electricity, but also other energy forms like gas or like heat using renewable energy sources. Most of them are volatile if we consider wind and sun, and therefore the integration in the energy systems, which is electrical or thermal or gas, is not so easy because of that volatility. Just for example, you see here how volatile is the generation from wind and sun. These are these gray lines, and you see how many times the system operators they have to use conventional power plants for redispatching according to the generation of wind and sun. Of course, the redispatching process is very expensive. So I remember that in 2016, the cost for redispatching in Germany were about 1 billion, so 1 billion euro. That cost are shared among all the consumers which live in Germany. At the same time, many times the system operator is not able to integrate into the grid the power generated by sun, the power generated by wind, and therefore they should be, so the wind turbine or the photovoltaic, they should be cut. And you see here how much energy from 2009 to 2018 has been or could be generated from sun, from wind, but could not be fed into the grid. Therefore, the idea is to use storage system for storing such amount of energy which could not be integrated, and to avoid, in this case, to use conventional technologies, because by 2050 we will not have any more conventional technology for integrating or compensating the volatility from wind and sun. So, among the scientific community, we have three solutions that are mostly researched. One of them is to have active consumers, which means consumer, mostly industrial one, but also residential, which actively participate to the integration process of volatility, which means that these consumers, they have to change their consumption behavior depending on when the power is generated from renewables. Another solution may be the multi-energy system, so the integration on having an holistic approach of what energy means, so integration on electricity network, gas network, mobility network, heat network, all that should be integrated as one very large system. And the last one is the integration of a storage system. Of course, the storage system may be part of a multi-energy system and may be also part or used for active consumers. So generally, the storage system are classified according to two criteria, namely the energy that they can charge and discharge and the power that they have. According to this charging and discharging power and energy, there are mostly two applications. The first one is for power application, which means I use storage system for supporting the grid operator to help the network stable or the frequency near the site radius, or for energy application, which means that I use storage system for storing high amount of energy that I cannot integrate in the grid in the time in which I could generate more energy, and I discharge this amount of energy in the time that I don't have enough generation from volatility from renewables. And you see here many sub applications that they can be applied, like demand side management, bulk energy services, tertiary control, primary control, etc., etc. Oh, among storage system, we have the first one, which is the most used technology, the pumped hydro storage. Such a technology is mostly used worldwide. It's also old. We have a different gigawatt installed capacity. However, at least in Europe, we don't have any more large spaces for installing new pump hydro. And beside it, also the social acceptance of population is not so high. So therefore, at least in Europe, installing new pump hydro is very limited as option. Another technology which we may use is the compressed air storage system. We have worldwide two such a kind of technologies, one in Germany and another one in US. Both these two technologies, or these two storage plants, are using the diabatic compressed storage system, which means that I compress air, consuming electricity, of course. I store air inside caverns, and when I have to discharge and to generate electricity, I burn also on fossil fuel. This is the diabatic application. Beside it, the last years is in planning near Magdeburg, where I'm speaking now, an adiabatic compressed air storage system, which does not use any fuel or any fossil sources for heating the compressed air. However, also such a technology is geographically limited because you need some specific caverns for storing compressed air, and it is still expensive. Batteries, we have in the last, I would say, 10 years or 15 years, is the maturity of this technology is improved. However, there are some concerns about the resources, the minerals, so lithium, for example, cobalt, which are required for manufacturing battery storage. So, and the main barrier of such a technology is they are still expensive, even if thanks to the immobility or thanks to the, I would say, mass production, the cost for power and energy capacity in the last year has decreased. The last one is the power to gas, which means to convert electricity into other energy forms, for example, hydrogen or methane. But I think that Professor Mulone will also explain in more details such a kind of option. What I can say that is from the point of view of efficiency, energetic efficiency is not so efficient, but from the point of view of the usage of other infrastructure, for example, natural gas infrastructure, it may be a very good option for the decarbonization process. So which kind of business model we can imagine to have for battery? So at Fraunhofer, we have both many years ago large battery with 1 megawatt on 500 kilowatt hour of energy capacity. Such a battery may be connected at 2 different voltage levels. And we have used such a battery in different applications, practical application. For that, we have learned if a business model may be exploited or not. One of them is here in Neu-Hardenberg, which is one, at that time it was the largest European photovoltaic plant. You see here, It is near an airport, old airport. It had an installed capacity of about 150 megawatt. And for this photovoltaic, we have integrated our large battery, so 1 megawatt, 500 kilowatt hours, for different applications, which I'm going to show you now. So the idea was to use the battery for supplying electricity during the night. So you have to imagine that this very large field needs also camera for security purposes, for observability purposes, for controlling, and such cameras needs a lot of electricity. So to sum all the cameras that they have. So the idea is to supply, to store the electricity during the day into the battery and supply the loads during the night. It was the first application. Now, the second application was in the network point in which such power plant, photovoltaic power plant is connected. The system operators many times have to curtail the generation. So the power plant operator cannot fit or could not fit into the grid. So the idea is instead to control the inverters or to control the power plant and cut the power, they charge the battery. So the system operator does not receive the power as predicted, and the power, instead to be lost, is charged inside the battery. The last one, since it is a very large battery, storage, a large photovoltaic plant, for this kind of power plants, the power should be sold to the market. There is not a feed-in tariff, normal one, but the power should be sold to the market at day ahead and intraday market. Therefore, the photovoltaic plant operator has to make prediction on how much power should be generated 24 hours later. On better such a prediction, higher is the bonus that they can receive from the system operator. Or longer are such prediction, higher is the malus that they can receive. For that, the storage system may be used for compensating or for improving the prediction error, and therefore to increase the possibility to have the bonus. So here you see just the idea how it works. So if the system operator does not is able to receive power, the surplus which could be generated is charged. The power before the sunset is charged for the night application, and this is the main idea. So for that example that I have shown you before, even if the user, the photovoltaic plant, had not invested on the battery, we have not identified any. So these three business models were not so attractive from the economical point of view, which could justify an investment. Not yet. Another business case that we have also investigated is the utilization of a storage system inside mechanical industry. This is the example of an industry which tests diesel generator, large diesel generator for heavy duty application. They make such kind of stress test in order to understand the robustness of the diesel generator. And the idea is, instead to waste the mechanical energy into heat, the idea is to convert the mechanical energy into electricity and to store it inside the battery. So also such kind of application, which seems interesting from the technical point of view, has been not interesting from the economical point of view, which has not justified the investment on the battery. The last one which may be interesting, which we have investigated from the theoretical point of view, is the business model called sharing economy. What does it mean? It means that if I have different users, which may be industrial user, which may be commercial or office user, or generation companies, if I have different kinds of users located near the same place, I can install a storage system which may supply different services for different users. The idea is I share the investment cost among the user, and my applications increases. So I have more applications, and therefore I may generate more revenue and more profit. So we have investigated 3 kinds of battery: lithium-ion, NAS battery, and vanadium redox flow, with a time horizon of 10 years for 3 different applications. Peak shaving for the industrial consumer, increase of self-consumption for the office commercial one, and schedule adherence for that. So it means that I improve my prediction in the day-ahead market. For this one, you see that also, for example, if I am an industrial application and I just use my battery for peak shaving, I could generate a revenue of about 9,000 euro. But if I share the investment among all the other users without giving the priority for peak shaving, I decrease also the revenue that I can generate. But if I control the storage system, giving the priority on the peak shaving, you see that the possibility to increase revenue from the same battery increases too. Now, if you analyze from the point of view of the generation company, as I repeat, so we have here wind and photovoltaic, and we consider just one application, namely to improve the adherence of prediction. I generate a revenue of about 70,000 euro per year. And in sharing economy, without giving any priority, the revenue increases to 20,000. But if I give the priority for using the storage for this application, the revenue increases up to 27 megawatt hour. Sorry, 1,000 euro. So you see here also how the sizing of the storage system with 3 kinds of storage system is affected, both in the case of a single application and in a sharing economy application. You see also which kind of internal rate of return you can expect it from different kinds of technologies, so NAS battery, lithium-ion, redox flow battery, or for different applications. You see that for generally the sharing economy application requires larger storage system. You see here in the power and here in the capacity. For single application, they require shorter or smaller storage system. So this is the last slide. So just concluding, the storage system, there will be a key element for the decarbonization process. Batteries may supply or maybe used also both for power application and for energy management application. Generally, if you want to make attractive from the economical point of view the usage of a battery, you should think to develop multi applications and not just one single application, because in that case it's very difficult to make the investment of battery attractive from the economical point of view. So this is all. Thank you for your attention.
Thank you very much. Now I would like to present Professor Vincenzo Mulone, from Associate Professor at Department of Industrial Engineering at University of Rome Tor Vergata. with the presentation of the challenges and I'm so sorry, hydrogen as a key energy vector in integrated small-scale distributed generation. Please. Oh, we cannot hear you. I think you are muted.
Okay, so first let me thank you for your invitation, and thanks to Dr. Lombardi for arranging this workshop. And today I'll try to give a talk which is more general in its scope about hydrogen. And then I'll try from one side to introduce you with some of the key features of hydrogen, that is the basics somehow to prove the usefulness toward 2030. And on the other side, we will try to show you some of the results we obtained in our labs in the last year on this very topic, and you know, show you a portfolio of our projects right now. Okay, so let's start from this, and in a longer perspective, what is really relevant for hydrogen is the fact that differently from the usual way of producing energy, that is due to conventional power plants along with a certain percentage of renewable to be used for residential or industrial or other applications, then of course things are changing a lot. So we saw in the presentation by Dr. Lombardi few slides about electric energy storage primarily, and this is however somehow something is a concept that is related to the grid itself, and to integrate and balance the renewable power plants, for example, you know, to integrate the photovoltaics during the night. So this is a typical energy application. Now the problem is that in the next year and probably with an horizon 2050 at least, we will certainly get to almost 100% of renewable energy in the mix, and also we'll have different scenarios in terms of transport. So transport will be more sustainable, and then aside of this paradigm of energy production and consumption, we will have the transport. And this transport will be sustainable. So we'll have electric vehicles and fuel cell electric vehicles, so hydrogen vehicles. Most probably will be a mix. Now the thing is that whenever the renewable should get almost 100%, and then we can get finally rid of the conventional power plants, the problem is that we will, in order to for the energy to be balanced, we need to have a lot of excess energy from renewables. But there is one alternative to this. So in order to avoid to install too much renewable, we can use hydrogen. And the reason is very simple, is that the electric energy storage technology is not scalable. So in order to increase the capacity, we need to increase costs a lot, first. And second, which is probably even more important, is that batteries, as we know from the everyday life, are subject to self-discharge. So after a few days of static conditions, so open circuit condition, the battery would naturally be discharged. And then this is a technology which is not relevant to swap, for example, the energy from the summer into the winter, which is a typical situation that can occur in our latitudes. So the solution to this is hydrogen. And Dr. Lombardi was talking about power to gas, which is of course one of the mainstream technologies for hydrogen. So we would use the excess of energy to run electrolyzers, and then we will have for sure local hydrogen storage that would be useful to serve other nodes, so to take advantage of this energy in other places and using the structure of gas, or to fuel the vehicles, along with the biofuels, along with the conventional fuels, most probably still running into place, and with the hydrogen produced from other sources. So this is a slightly more complicated scenario, but the rationale is just as we thought. So in order to avoid an excess of renewables, which would get into either a massive installation of photovoltaics and wind, or the curtailment, as also Dr. Lombardi was saying, then hydrogen is the perfect recipe to that. Then, is this a smooth transition? No, I don't think so. It's not really smooth. But let me show you a few of the characteristics of the technologies that are behind. So first, let me talk about large-scale projects for hydrogen production through electrolysis, which is one of the most important technologies, very clean and very efficient also, by the way. So we use water, and through the absorption of electric energy from renewables, of course, we can produce what we call the green hydrogen. Then the green hydrogen depends, cost or economy depends a lot on the cost of energy. And also we saw in the first presentation today the figures of the energy for the photovoltaics, which is pretty much in the 8 cents per kilowatt hour, per unit kilowatt hour. Now, depending on the technology we want to use for the electrolysis, we have different figures in terms of costs. And this depends on the current cost of this technology, of the electrolyzer. So we can hardly go below 3 euros per kilogram, which is, of course, a cost which is still pretty high if compared, for example, to methane. But if we understand the advantage for this society and for the strategic asset of Europe and of our countries to get into such kind of business, then we understand quite easily that this is this raise cost must be leveraged, you know, with the other advantages we could get from what I told about in the last slide. So, however, these are the figures, and this is very important to figure it out. This project, which is Refine, is a project funded by the FCAH-JU, so it's the joint undertaking for fuel cell and hydrogen. Is a 10 megawatt project, so the electrolyzer is already pretty large, and it is gonna end by the end of 2022. But also there are other options for the production of hydrogen. One is that I consider preferential is from biomass. So there is the chance of producing hydrogen from biomass either through a gasifier, and this is a rather simple technology consisting of a sand bubbling bed, which is flown with biomass. For example, we can think about waste, so food waste, or any other kind of waste, for example, from residues of operation of factories and so forth. However, waste in general, then we can, of course, you know, get into more detail about the yield we would have in terms of hydrogen. However, the bottom line is that this technology, along with the steam, so with water, can produce a mix of gas. And in the figure on the right, you see with the green bar the percentage of hydrogen, which is already pretty high. So we can produce a gas under certain condition which has 25% in terms of energy of hydrogen concentration, sorry, which is pretty high. And then there are technologies to then concentrate the hydrogen and then produce a combustible mixture that is compatible with the one that is, for example, produced by the electrolyzer. Or another technology which is more innovative is this one. So starting from woody biomass, through the pyrolysis process, we can produce bio oil. So it's kind of it's similar to diesel fuel, but it's not combusted in vehicles. It's just flown through a reformer to produce hydrogen. And then another technology which is slightly more complicated. It's a triple reactor with iron oxide, which is flown through the 3 reactors in order to get from the biochar, which is a sort of biocoal, to produce again hydrogen. So the 2 things at once allow to produce hydrogen again, starting from biomass. And on the right, you have a graph which is inspiring, in my opinion, because here for the positive figures on the y-axis, so from 0 to 30, we can understand that this the energy balance for the reactor is even positive. So this produces somehow energy, while it absorbs energy whenever we get the reactor at this temperature. Now, the reason why I show you this graph is to tell you that we have flexibility, so we can produce a different amount of hydrogen, so we can maximize the yield as long as we provide energy to the reactor. But the budget is positive in most of the cases, so out of the biomass we can simply get hydrogen. Of course, it's slightly less efficient than in the case of steam methane reforming, so producing hydrogen from methane, which is the mainstream technology right now today. But in case of methane, it's a fossil fuel. In this case, instead, we're talking about a green fuel, since it is otherwise a wasted feedstock. Okay, talking about the utilization technologies, then let me just show you a few figures of the fuel cells, and they are the mainstream technology for the utilization. One of the key aspects of fuel cells is their efficiency. So they are much more efficient than conventional internal combustion engine. The efficiency can be a figure greater than 55%. Depending, however, on the design of the fuel cell. And this can happen already at a relatively small scale in the range of 1 kilowatt. The problem with fuel cells is still the durability. So the targets we have from the automotive application is at least 8,000 hours of operation, and from stationary system a requirement of at least 40,000 hours. And this is still hard to attain. So this is the problem we need to solve. However, in the last 10 years, costs have been reduced by 60%. So already today, if compared to 10 years ago, we have a cost for the fuel cell which is almost affordable, but durability is still a problem. And the cost, or better, the cut of costs was mainly due to the optimization of the use of noble metals. So platinum is a major component of fuel cells, and then we learned in the last 10 years how to exploit, how to use much more effectively a given amount of platinum inside fuel cells. So on top of this, there is another aspect which is of primary importance, is the fact that, for example, a vehicle, but this is also valid for a stationary system, it is not only equipped with fuel cells, but also with what we call the balance of plants, or auxiliary systems that need to be optimized, need to be integrated with the fuel cell. And we're talking about the tank, a battery pack, because a fuel cell vehicle always requires also a battery storage system in order to avoid early degradation of the fuel cell itself. So it's at the service of the fuel cell. And power electronics, the CDC converter, cooling system, which is peculiar as the operating temperature are fairly low and very different from the typical temperature of a combustion engine. And of course, the electric motor that, however, is already developed in these years due to the widespread use of electric vehicles, even today. So this is more a slide commenting on opportunity that would arise from the diffusion of fuel cell hydrogen electric vehicles. Then what I'll talk about in the next slide is instead a stationary application, and it was the case of a project we developed in a few years ago in the telecom sector that was chosen as an application for the relatively high value of energy. If we understand that for off-grid sites that are thus not served by the electric grid, the energy would acquire a value that is much greater than the cost figure we were talking about at the beginning of this talk. So this gives room to use more sophisticated technologies to provide energy continuously at a given site during the year. Let me also, as we speak, tell about our group. If inserted in this background, so working on hydrogen, but we have a pretty large group with colleagues, professors, and students, and these are some of the companies and the institutions we have been working with. And we have a lab where we test all the systems we talked about. So here you can give a look at the system we have right now in the lab with a triple fuel cell stack with a hydrogen alkaline electrolyzer here, and power supply and electronic loads which are directly connected to a weather station. We have to acquire data and emulate a photovoltaic power plant and batteries. So this project I was talking about was a demonstration project. It was fairly big, and we had on board two of the telecom provider in Italy, so TIM and H3G at the time, and also we had on board the consortium leader Ericsson, who was providing the technology for the radio, and Danterm, today it is known as Ballard Europe, MES producing the fuel cells, Green Hydrogen producing the electrolyzer. The idea was to provide energy to the radio, to the telecom radio, from photovoltaics in this order of magnitude of power output. The problem is that whenever you get at night for an off-grid site, you can certainly use a battery package to swap the day and the night. But problem is, especially during the winter, you can early run out of energy, and what you need then, as I told at the beginning of my talk, is to use hydrogen. So this hydrogen can be converted into the fuel cell to produce energy to be consumed at the radio. And whenever you also have, for example, in the summer days, an excess of energy from the photovoltaics, this energy can be used not only to charge batteries, but once the battery is fully charged, you can produce hydrogen, which is then back used in the winter days. So with this simple layout, you can easily swap the otherwise curtailed energy from the summer into the winter. And we had 13 demo sites, and we published a paper where we just gave a few numerical results, few more details about what I was talking about. And I would just want to make the long story short. this paper is a lot about the typical situation we get in a few different days in terms of the power flux at the different components of this system that we call a hybrid system. It is hybrid because you have a mix, you know, of photovoltaics, hydrogen, and hydrogen produced from the electrolyzer, but also hydrogen produced from steam reformer that is stored in bottles and taken and brought at the site directly. So hydrogen is also hybrid because a fraction comes from renewables and another fraction comes from the fossil sources, as the mainstream technology even today for the production of hydrogen is through methane with the steam methane reforming process. Okay, so in a bad weather day, you have a very fluctuating photovoltaics, so radiation at the photovoltaics, and given the load of the radio station, which is fluctuating but not that much, then you need to provide this continuously, and this calls during the night, because this starts from midnight, for the power produced by the fuel cell is the red symbols, and then whenever the sun comes up, then you have a reduction of the fuel cell load, and the radiation going to through the photovoltaics and then producing power that gives the counterpart. It's very few of these coulombs, so a tiny fraction of this energy can be used to recharge the batteries. The batteries is in blue here. It is totally different than a good weather day where the fuel cell still runs over the night, but then it shuts down until midnight again, because the sun is so high that the battery can be recharged quite effectively, and then we can use it during the early hours of the night to provide the energy to the load, which is still pretty much the same at this level of ampere absorbed. The average weather is in between, you know, so you still need to turn the fuel cell on earlier than what you see in a good day. So from what you can understand already looking at this situation, whenever we talk of renewables integrated with hydrogen, the optimization of the system is very complicated, because what we see is a situation that changes radically even day by day. And whenever you design the system, then you need to consider this in advance. So we have in our group developed simulation tools that help to design such system in order to maximize the performance. But even the definition of performance is not very easy, because you can read in the paper the results, of course. Then depending on the specific site, and this is a specific characteristic of the telecom application, you have a consumption of energy which was extremely different. For example, we had in these 6 sites a very variable consumption of energy during the year, and this is due to the fact that the radio apparatuses have different technologies everywhere you go, and then depending on the specific site, we had to design the system in a completely different manner. And then again, the simulation and modeling tools were very, very useful. What we understood, and it was written in the paper, but I want you know, many details about this, since I don't want to spoil the presentation. We needed to understand better how to compare systems characterized by different energy consumption. And then we found out a few results telling that, for example, in this case, site number 4 was consuming the lowest amount of fossil energy sources, but among these 6 systems, there's no one with electrolyzer. But then adding the electrolyzer was a chance more to produce, to consume, I'm sorry, even more fossil energy sources during the year. So with the electrolyzer, and this is quite obvious, however, if you think about it, if you design correctly the electrolyzer, you can practically use energy which is completely green at the site. But this is slightly, I mean, not even slightly, this is more expensive than instead getting rid of the electrolyzer and bringing the hydrogen at the site, which is all the other 6 cases, over which, like we said, case number 4 is the best case in terms of decarbonization, so of decarbonization itself. Yes, that is a good word. Now, just to end my presentation, I wanted to get back to economic figures, since one of the main outcomes of the project was to detail a cost scenario, so a business model. And what we understood was that the hydrogen fuel cell systems, if compared with the diesel generator, which was the mainstream technology to provide energy at an off-grid site for telecom applications, then it was much more expensive at the very beginning. But then it came back quite neat due to the fact that the fuel cell efficiency is much higher than in the case of a diesel generator, which is a small engine and it's fairly inefficient. So we could get the break-even very soon. One of the reasons why this project was so successful is, of course, due to the leverage effect we could gain for the energy. And then another important conclusion of this study was that whenever you added, and this is the red line, the electrolyzer, then of course the costs were much greater at the beginning. So the cost is almost doubled whenever we consider the electrolyzer, but the break-even is moved toward the 5th year instead at the 2.5 year. So the bottom line is that if you need cost effectiveness, then the production of green hydrogen is not really the choice in this case. But if you want to prove decarbonization and then maximum effectiveness in terms of decarbonization effect, then you can consider the electrolyzer without spoiling the cost too much. So the break-even at 5 years is still almost quite sustainable, I would say. Other projects we are running on hydrogen are these other ones. So there is I2Rail. It's a project that we have been funded with by FFPA last year, and we are retrofitting a diesel locomotive with a fuel cell system. This is a very thrilling project where we provide support for the design of the solution and of the fuel cell with the hydrogen storage tanks and the cooling system and all the balance of plant we are talking about. And we are very proud of it, of course. And hopefully, you know, this also would help for the decarbonization of the railway sector, which is very peculiar because the diesel locomotives are still a considerably high fraction of the full ones all over the world. If you think about all the different countries where railways are developed, and if you think of very different infrastructure and distances in countries other than Europe. This other one, which is in collaboration with Fraunhofer IFF, it's a match for you. Hydrogen will be considered here most probably as a benchmark, so to compare and to get comparison whenever we consider other technologies. These are the projects instead about the development of a smart energy hub for the storage in general, and then of course we will also run into the consideration of hydrogen. our university, along with Iveco, is the Italian consortium, and we will tell more about smart city, and this were inactive the last year. So with this, I just concluded my talk. I hope it was clear enough. If not, just feel free to email me with anything you should have. I'll be more than happy to whoever. Thanks much again.
Thank you very much. And our last presentation for today, Dr. Christoph Wenge, senior researcher at the University of Applied Sciences Magdeburg-Stendal, will talk about challenges and advantages of electromobility for the grid integration. Dr. Christoph, can you hear?
I hope you can hear me now and
Yes.
see the presentation.
Yes.
Wonderful. Yes, I think I will short my introduction a little bit because we have heard already the motivation of the fact that we are working on regenerative energies, and also the fact that we want to electrify the mobility. Very shortly to myself, I'm since 2008 working with electromobility, with mobile and stationary storages. As Dr. Lombardi already showed, this big battery storage was one of the projects I was working on. But today I was asked to talk about the e-mobility. I think it's quite clear that we have local and global effects which motivate us more and more to change from the conventional energy resources to the regenerative energy resources. Also, the e-mobility is one aspect because the mobility sector takes part a lot on the particular matter, for example, and the NOx and CO2 pollution in big cities and in the area. And this causes different effects from climate change till sicknesses of the people which are inside of this environment. The regenerative energies, as we have seen before already, they are the generation of them, they are not available all the time. And if we see that e-mobility comes through, we have additional big load inside the grid, which is also volatile and which can also give or stress the electrical grid. So we see on the numbers that in the last years, the amount of different electric vehicles and plug-in vehicles on the market are increasing. And if you look at the numbers in the futures, we will have about 128 different models which have electric traction. And this shows us that there's a lot happening over there. The question of this electric vehicle is not only to have the traction electrified, we need to have regenerative energies, which I will show later on what solutions we are working on to combine the regenerative energy generation and the demand of charging electric vehicles. So what we can also see, the number of electric vehicles is increasing too. It's not that high right now. 1.2% is with electric, like plug-in hybrids or electric vehicles in Germany. But the number is increasing a lot, of course, of the market situation right now that we have different models over there. But when we're talking about the vehicles, we have to talk, of course, about the challenges charging the vehicle. This is a problem too. Everybody who is thinking about electric vehicles, especially in industry, most projects we were working on are not the commercial electric vehicle We are working on fleet operation. That means that we have electric vehicle fleets, lots of electric vehicles, which are on one place, and of course, most of these companies using them in logistic. So priority is that you always have the possibility of mobility. You can't cut over or accept any additional charging times or to limit the availability of the mobility. So there are questions which appear. The number of charging stations is increasing too. And the two biggest questions and challenges are, like I said before, the charging station. Where do I place the charging station, and the demand of charging stations? For this, you can define the general questions we had in our different projects. How is the range of the electric vehicle? Was the first question to fulfill my tasks which I have. If I look at logistic companies, or even we have projects now where there's the ambulance cars to electrify the ambulance cars, then you have a high priority of mobility of these vehicles. That means they have to run, and they have to at least fulfill the requirements for their work. And to do this, you're analyzing the fleet. How and where can I charge is the next question. If I don't have a central place where I can charge them after I use them, might I have to charge during my tour or my trip I'm doing with the vehicle? What charge infrastructure do I need is a very big question because of the investment. If I'm thinking about 50 cars or 20 cars and I thinking on fast charger, then this exceeds very fast the limits, the capacity of the electric connection of the location. And the advanced options, which is more interesting, is the question, what potential do I have for additional integration of the electric vehicles? Can I combine them with my system, which we had seen before by the presentation? That means combining them with PV, combining them maybe with a local generation, PHP, and how can I connect them to the infrastructure? And also a very interesting topic is, might I can make ancillary services with my electric vehicle? This is, we have projects to this too. What is necessary for this? And of course, one electric vehicle might has no that big effect. But if I look at fast charger, which have 50 kV and more, or if I look at EV fleet, then I have a capacity which I could use in the grid. I will hurry a little bit up on this. I think I have said already, you have to make the analysis, means general fleet profiles. So we made this with GPS tracker in different projects. Then you analyze the need of load you have on the vehicles, the distances, the time to charge, and so on. And at the end, when you have all these data sets, you can make profiles, as you can see small over here. And out of these profiles, you can look where is the gap to charge. And you can see what flexibility do I have in my system to use my electric vehicle as a storage, as a flexible load. If I look in future technologies, which we have in other projects too, might I can even use my vehicle not as flexible load, I can use it as fully battery. That means I can feedback energy in the grid. And might I even able to do this phase selective? That means I can look which phase has already the capacity of this line is full, then I just change to another phase of the electrical AC grid to fully use the capacities. Fast overview, we have the question between fast charger, which is more than 50 kV, and we have the slow charger. This will be the standard electric grid, single phase or three-phase system. And I just translated this here. You see like standard like 15 kilometers an hour. You can charge with a 3.6 kilowatt. And this will be 100 kilometers you can charge in an hour. And if you have a DC charger, you can charge even 200 kilometers and more during 1 hour. Yeah, just more or less fast calculation about the possibility. Out of these different projects, I have just one fast example over here. We have seen that in the analysis of the fleets that the 90% of this cases or these vehicles in these cases we had, they had less than 80 kilometers in the tour, and then they returned to their place and they had been available to charge or to even do grid services or to offer flexibilities on this place. You have a high potential for demand side management. The potential is very high to integrate regenerative energies. In this project, we had the possibility to combine CHP generation, PV generation, and big loads because this was like a press, how's it called, newspaper and logistic company. And they had big machines over there, and they had a big fleet of vehicles. So this was an interesting combination. And then you can check and simulate this and look how much is the flexibilities and what infrastructure do they really need. A further step, which is future research, is the ancillary services of with electric fleets, which I try to fast go through. We can divide the ancillary services by frequency control, ancillary service storage for voltage control, and you have this different services under this group, which could be done with electric vehicles or electric vehicle fleets. The electric vehicle, the only thing which is interesting for this service is not all these complicated components. It's actually the charger, the battery, the charger, the battery, and the connection. We have the battery system. This will be the storage. We have the charger. This could be inside of the fast charging station or inside of the vehicle, which is normally the slower charger, like an AC charger. And the grid. And of course, you need some other instance which is giving the information and managing everything. We have the managing of the storage will be inside of the EV, and the managing of the requirements to keep the fleet running, that the charging will be in a higher instance. And the energy flow is all depending on the charger. So what ancillary services could I do? Might I go not in detail because time is pretty low, not much. I have the active control, active power control, reactive power control, phase selective active power control, and reactive power control I could do. And distortion reactive power. That means that you can look for high frequency distortion in the grid and compensate them. This could be done by the power electronics, and you see over here the different effects in the grid. In our laboratories, we have for this, you have like two main focus over there. One is the hardware to fulfill the requirements, that means the power electronics, and the other thing is to combine this in the actual standards. That means you need the communication, which are going through the 15118, the high-level communication, and the other thing is that the charger has to be enabled to do these services. The charger itself looks like this, that we have 3 single charging systems This is one possibility for power electronics. Of course, there are other possibilities, but like this, we're able to have run each single phase be bidirectional, and we can support reactive power and active power by each single phase. At the end, we have in the laboratory the possibility to have the flexible load or storage system. On the other side, we have the grid. And then we have the communication with the actual standards and the mobility area control center, for example, or an energy management system, which could be local or global intelligence, telling the vehicles or the storages how to behave in the grid to do the maintenance. For this, we have different test systems to test battery systems, to test the charger systems, and at the end, the aim is to create a battery system which can be used as a black box storage. That means all the functionalities which are not really relevant for the higher level system, like the operator, should be done in the local system, and you should have standardized interfaces to the upper level, and you have to fulfill the requirements of the grid or of the crest you get from the upper operator. For this, you have the possibility in test benches to look at the cells, for example. This is a very interesting part. But the question is, what really happens in the cell? And we had lately an interesting project where it was the idea to look inside the cell. How can you look inside the cell? This was done with fiber optics, and our partner had the measurement systems over there. So you have a fiber spectrum which is going through the cell. You have over here the sensor, and then you look at the reflection on the other side. That means you look at the spectrum which is coming through the cell. In this application, you have to, of course, connect this fiber optics over there, which are really skinny. I guess some of you have seen this already. This is like a hair that big, and then you have to look that there's no cracks by the installation. And when you finally get this installation, then you don't have only the standard electric parameters, which you can measure on the clamps of the cell. You have additional information of inside of the cell. And this additional information, they give you the possibility to see how is my cell right now. Is it how's the state of health, for example? How's the state of charge? State of charge is normally measured while charging and discharging, and when you stop charging or discharging, then the voltage is very slowly going to the relaxed voltage level, which you can see here, over here, the gray one. That means you don't really know in this moment how is the state of charge or state of health of the cell. And by looking inside of the cell with this spectrum, you might see additional information, and you can increase the information of your system, and you can increase the possibility of using the battery system, which means that you will lower the cost of the battery system, because right now you're limiting the battery systems, the possible capacity of the battery system to not damage them. You make the limits a little bit lower, to be in an area to not stress the cells too much that they're aging too fast. And with this, you really know what is happening in the cell, and you could exceed this, or you could think on second life and so on. So it gives you better possibilities. At the end, it's even interesting for the insurances, because when you have battery insurance, they of course want to know how big is the risk that the battery is going to be damaged. Yeah, so this is a fast excurse in all the different projects which are related to the electric vehicle, because when I have high density storages, I have one big problem. which I forget to mention, that we have the storages in the electric vehicles are just have not enough energy density. Right now, it's good for city transport, but if you have long distance transport, you have little problems to fulfill all the requirements. Yeah, and this brings me to the end of my presentation. So electric vehicle, of course, has an increasing influence on mobility sector. We need, of course, smart infrastructure and we need communication to integrate electric vehicles over there. We need technologic innovation, what we have to have in the storage and in the charging infrastructure to become better with electric mobility and reach the possibilities we have right now with the standard combustion engine. Green energy supply means at the end that we have to make our energy management system smarter, and we have to couple all different sectors, which we have seen already in the other presentations which we have seen before. Yeah. And to drop the last few words, because I'm now today here with the University of Applied Science in Magdeburg. We have over here also different applications which consist like a test bench for battery system, e-mobility center, which where we have researched on the points which I presented you already, and different regenerative energy supply like wind and PV. And what we are building, what we want to have in future is hydrogen microgrid development and a small test lab, and also bigger PV generation and newer wind generations, and combine all this to a multi-energy grid, small multi-energy grid to supply heat, to supply electricity, power, and of course to have mobility all connected together, couple these different sectors. Yeah. Thank you very much, and I will be open for questions.
Thank you very much. Now it's time for our roundtable of question or discussion. I saw one question from Francesco on chat. Francesco, are you satisfied with the answer, or you need to follow up?
No, for me it's fine. I mean, if Pio wants to give some more details, it's okay. But I knew it was going to be it depends because there are so many factors that plays into this decision. But it's a difficult task to decide what's the optimal sizing.
Are there any questions from the audience? If not, yes.
Janet, just one precision to Francesco. So when we talk about sizing, generally we have to always to understand that in the battery we have two dimensions. One is the power, and the second is the energy capacity. So the size and battery or storage in general way, it means that we have to decide the power capacity, so the power capacity for charging and discharging, and the energy capacity, which is as the time, how much time it takes to charge and discharge energy. So two dimensions, and they are not dependent. So generally for battery, the investment cost for charging, so for the power, is different from investment cost for the energy capacity. So, and therefore, it's not so easy to size in the best economical way. I just want to point out it.
Thank you. Dr. Wenge, could you answer us this very interesting question? Which barriers do still slow down the development of mobility, in your opinion?
Which what?
Which barriers do still slow down the development of the e-mobility, in your opinion?
The general barriers are first the acceptance at the people. I think this is slowly changing because more and more people tried e-mobility, and it's for city transportation. I have seen them more and more. And the next thing is the technological barriers is the charging infrastructure, especially for the city. If you don't have an own house or the possibility to charge somewhere, you have a barrier to buy an electric vehicle because you can just use it. And the storages, I think too, because we have to become way better to reduce the CO2 for producing the battery systems, and the values of energy and power intensity of the storages have to be increased.
How do you think this acceptance from the society can be reached faster?
I think a high barrier is that some of them are scared of the technique. I think this people become less and less because they are in touch with the e-mobility systems. And the next thing is the price. The prices are still higher than a standard vehicle, and people are a little scared because they see from the smartphone the battery is not that long lasting, and then you have a battery which is a few €1,000 worth, and might you drive the vehicle 5 years, and at the end you have high risk that you lose lots of investment. And I think this is a barrier to the storage itself to become better over here, to give more security to the people.
Thank you. Pio, could you answer what are the conditions which might make the usage of energy storage system economically attractive? In your opinion, what will be the conditions?
Okay, good question, Anita. So it is not, as I said also to Francesco, we don't have a general rule which may justify for all the cases to use storage system. However, we are also making a project, European project, in which storage system may be interesting for a manufacturing company. So supposing that you have, for example, an factory, and you also produce electricity using photovoltaic, for example. So in the case in which you don't receive any more incentive for feeding the network, it means that the time, so generally in Germany you have 20 years for feeding tariff. After that, you may feed the network for free, so you don't receive any money. In that case, increasing the self-consumption using storage system may be attractive, maybe a solution. So that it could be a scenario. So in all the cases in which you can increase the self-consumption, I see a lot of potential, but not all the cases can justify an investment on storage system because they are still expensive. So only because they are still expensive.
Thank you. Professor Mulone, could you specify which is the most promising application amongst all you described during your presentation?
Okay, thank you. And okay, so we presented a number of different applications, but as I highlighted in the presentation, one of the most important aspects to be considered is the intrinsic added value of the service you want to provide. So from this respect, I think that the automotive sector is one of the most important cases for the value you can give to the fuel itself, which is I think one of the most exemplary things. So I think that from that standpoint, of course, also solving the problem of the infrastructure, then the automotive sector can be one of the entries. Then I also think that the industrial application can be very relevant. And I think from that standpoint, the mechanism can be different, because it's not really a matter of the energy that is one of the lowest costs for industrial applications. As we know, that there are incentives. But in that other case, I think the incentives for decarbonization can be the key. So I think also that all the investments that have been done formerly for the increase of energy share from renewables can be even more effective with the further investment of hydrogen to increase resilience, to increase decarbonization and so forth. So with a very different philosophy, the industries can invest in hydrogen with the support, of course, of government in order to implement strategic actions for Europe and for our individual countries.
The government support is always a difficulty, at least in
Yeah.
Poland here.
Yeah, true. It's difficult, but it's not. The difference is that you can really get independence on the fossil sources, which is almost impossible without hydrogen, because you would need you would have a lot of curtailment energy, which whenever you go toward 100% would still wouldn't allow to get you rid of fossil sources. So this is not really evident today, but it will get very evident whenever we move to a different share. And also Denmark was an example from this standpoint, for example. They started to produce hydrogen with the curtailed energy they had from the wind, from the larger wind farms.
Do you think there's still also some acceptance from society issue also with the hydrogen, or do you think it's not a problem?
So it's a twofold answer. So I don't think that is a real problem first, but still there is the problem of acceptance, especially due to the high pressure of storage tanks. So which is of course which needs some iteration, which needs more sensibilization testing and dissemination in general, which is what we're doing also today. But methane has similar problems. Is not really less dangerous than hydrogen. And also there are technologies to store hydrogen at smaller pressure, of course, with different capacities, but still they are there. Metal hydrides, for example, or even the case I was talking about for a smaller scale system, biomass. So you can just produce hydrogen whenever you need, and then store the hydrogen in the biomass. That is another example, that can of course be a side of the mainstream industrial electrolysis process with large scale projects. So I think there is room for pretty much each of the cases I was showing today.
What is, in your opinion, the ideal combination between conventional energy storage and hydrogen-based technologies?
Okay, so as I showed in a picture, was the picture of the car. Hydrogen system would systematically call for electric batteries. The reason is very simple. Batteries are much more efficient in storing energy because they don't have the inefficiencies of the turnaround, electrolysis, and the use of hydrogen. In fact, we need to highlight that hydrogen is not available in nature. We need to produce it, and this is apparently a conundrum, a violation, of convenience. So with this in mind, we always need batteries to store energy because this is the most effective action we may do. in a small time horizon. So one day to the other one, and that's it, because we talked about the discharge problems. So energy-wise, this is relevant, and then hydrogen would always call battery aside. For automotive systems, there is also another important thing to highlight, is the fact that automotive, that cars are subject to very variable requirement of energy. And this is not good for the fuel cell, which is weaker than batteries today. So we need to preserve it. And then what we may take advantage of is the fact that batteries can give a prompt response to take the load, and then fuel cell instead can go smoother over the load, just to make sure that we reach the number of hours I was talking about in my presentation. So it still depends answer, as Francesco told, but the application is very different. So in one case is for efficiency, and the other one is for durability.
Thank you. If there's any additional question from the audience, please feel free to ask. And Ms. Dornhofer, could you describe a bit the life cycle cost of this own microgrid that you presented?
Yeah, we made the calculation with the together with the municipality, the whole investments for the new PV panels, for the diggings, and also for the whole electrical network and for the energy management system. And the life cycle calculation is about 12 years for the municipality that the systems will be economical. Excuse me, I cannot hear you very.
I'm so sorry, I muted my microphone and I couldn't talk. Thank you for your answer. Are there any questions from the audience, maybe? If not, we can close this session today. Thank you all for all the presenters. Thank you for your time, and thank you for the audience to stay with us. And I hope to see you all in our next workshops. Thank you, Pio, for organizing this session. And have a very successful evening today.
So I'm sorry, Zanetta, probably Christoph had a question on hydrogen again.
I'm so sorry, I didn't see that.
I don't know if it was addressed to me, but I can answer.
Yes, I had a question, but it's actually, I can read it. The question was, do you think the efficiency of the H2 storage is like the biggest barrier related to the storage systems? And what do you think, where will we end up in the future with the efficiency of this technology?
Well, the efficiency of the storage itself is of course limited, but it's due, for example, to the energy required for the compression, is due to the heat losses. So there is, of course, improvement there. But one of the intrinsic problems is that whenever you just use the energy to produce hydrogen and then back into the fuel cell, then you have a penalization which is even greater, because you with 0.6 you have 36% efficiency. It's just, you know, numbers are given as an assumption. You have 36% turnaround efficiency, which calls for 64% wasted. You know, if you increase then with the efficiency of the storage system, you can even go lower, which is quite small, but still much better than curtailment. But to answer the question, then I don't think that the efficiency of the storage system is really the bottleneck. I think the safety of the and cost of storage system is not the bottleneck, is the enabling factor better than the bottleneck. I hope I answered, Christoph.
Yeah, Mike, we can have a more detailed conversation about this in another round. Otherwise, we will bore the people over here.
Absolutely. But still, I didn't want to miss the question. So.
I'm so sorry. I didn't see the questions. Please interrupt me if you have any. Please, I will check the chat again.
Are we going to make a picture of the people again, like a screenshot, or?
We have a recording, so we don't have to. If nobody wants to show yourself, but if you want to show yourself, we can take a picture for sure. So if anyone turn on their computers, please. And I will make a screen here. 4, 3, 2, 1. Fine. Thank you. Thank you for this. Okay, thank you again, Pio, for organizing this session. And I hope to see you all in our next one, our last one. And have a, again, successful evening today. Thank you for all the presenters.